Good afternoon, and welcome to the third talk in the Carnegie Observatories 2021 Spring Astronomy Lecture Series. I'm John Mulcahy. I'm the director of the Carnegie Observatories and the science deputy for the Carnegie Institution for Science. We're streaming again live from the Huntington today without an audience, so we do thank all of you watching from home. I do want to also take a moment to apologize for having to cancel our last, or postpone our last lecture 2 weeks ago, but I'm happy to report that we've rescheduled that one for June 7th, so it's 2 weeks from today at the same time, 4 p.m. Pacific time. So hopefully you will join us for that. I want to start, before we get going, to, as always, acknowledge support for this lecture series from the Norris Foundation, and to thank our friends at the Huntington for helping host us for these lectures. Today we have a very special speaker. We have Ilva Guthberg. Ilva did her PhD work at the University of Amsterdam before coming to Carnegie a few years ago. She first came to Carnegie as a prestigious Al-Nashman theoretical astrophysics fellow. And then last summer, she was awarded a Hubble Fellowship to continue her work at Carnegie. And so she's currently a Hubble Fellowship and will be around for a few more years. So we're happy to have her stay a bit longer. Ilva works on the important topic of binary stars. Most stars in the universe do not occur in isolation, but occur in pairs, triples, or sometimes even higher multiple systems. The sun is a bit rare in that sense, that we have a single star. But as you'll learn today from Ilva, being a part of a pair really does have an impact on how a star evolves. And so without further notice, let me introduce Ilva Guthberg to the stage. Thank you, Ilva.
Thank you very much, John, for that very nice introduction. Sorry, let me just put my glasses. Today I'm going to talk to you about stars. I work with stars, and in particular stars that are in multiple systems, something that we can see in the background of this first title slide. So you may have thought that stars are spherical, right? But here we have a completely different picture where interaction is occurring between these two stars. So let's take a journey through cosmic time as the stars dance together in these binary systems, a journey of helium stars. So what if I would say that stars made out of helium have played a crucial role throughout cosmic time since the universe was very young? They provided a large amount of ionizing radiation, this highly energetic radiation, and also particularly contributed to create gravitational waves. Would you believe that? Are helium stars that important? Have you ever heard about a helium star before? Or is that something new to you? This leads me to my outline of today, where I'm first going to tell you what is really a helium star, how do you create one of those, and what about those ionizing photons, why does that matter, leading to the gravitational wave emission, can they be an alternative source of gravitational radiation, and finally my favorite part, a new discovery that we are about to publish at Carnegie Observatories of stars stripped of their hydrogen-rich envelope, the helium stars, a first population found in the nearby Magellanic Clouds. So let's start with what is a helium star? I think to answer that question, we have to go deeper. We have to go to, what is a star really? I will argue that a star is a factory of elements. It creates, for example, the oxygen that we need for breathing. But to fully understand that, let's ask a different question. What is a star made of? What is it composed of? This hasn't always been well understood. In fact, about 100 years ago, this very famous astrophysicist, Henry Norris Russell, in 1914, claimed here in his quote that if the Earth's crust should be raised to the temperature of the sun's atmosphere, it would give a very similar absorption spectrum. The spectra of the sun and other stars were similar, so it appeared that the relative abundance of elements in the universe was like that of in the Earth's crust. So Henry is saying that stars are just big Earths, that if you make something as massive as the sun, but as the same composition as the Earth, you have the sun. So this is wrong. This is something that Cecilia Payne-Gaposchkin, in her PhD thesis, disproved. Cecilia observed stars and found, no, they are mostly made out of hydrogen and helium. So it was a very strong claim at the time, in 1925. So she actually doubted her results. But today, we know that Cecilia was very right, and most stars are in fact made out of hydrogen and helium. Why is that? Let's go really far back. Let's go back to when the universe was formed. In the early universe, as a consequence of the Big Bang, hydrogen and helium was created. And those atoms clumped together in smaller clumps. And as this accumulation proceeded, you got some overdensities or so. So you will have to see this as a small cartoon, because you need, of course, many more atoms in order to create a star. But this is the main idea, that from hydrogen and helium, you get overdensities, and this becomes a star. The star, at the beginning of its life, starts to create helium out of hydrogen in the center. It does so by combining 4 hydrogen atoms into a helium. And this is a reaction that is giving you a more stable outcome, so therefore energy is released. The energy is released in terms of photons, so this is the reason why the star is shining. Right? So, but eventually, fuel is going to run out, right? There is only so much hydrogen. So you end up with a helium core. You could also see here that the star expanded a little bit as a consequence of the creation of a helium core. After this stage, it continues in a similar manner. You create carbon and oxygen out of the helium, create a carbon-oxygen core, a silicon core from the carbon and oxygen, an iron core, and eventually the star explodes. In the supernova explosion, this is a cartoon here again, and you can expel this material now into the interstellar space. And this is also one way that we got oxygen on Earth. The end product is a neutron star, or a black hole, for this massive star. And we will get back to those objects later. But for now, let's look a little bit closer at these 2 stages. I want you to notice 2 things. First, we have the creation of a helium core. Second, the star is expanding as a consequence of the creation of the helium core. So in this cartoon, I assumed the evolution of a star that evolves in isolation. But in most cases, actually, this is not the case. This is more common for the massive stars. The 2 stars orbit each other in a binary system. And what happens then if one star starts to expand as a consequence of the creation of the helium core? This is what we're going to witness in a little bit, but the movie is maybe a little slow. There. So we enter this phase of when the system is no longer composed of 2 spherical stars. We have mass flowing from one star to the other star is growing in mass. And eventually, as the outer layers, these hydrogen-rich layers, are accreted by the second star, what is left is just that hot and compact helium core. So let's just go through this a little bit more. What just happened? We had one star orbiting another star in a binary system. And the most massive star, it creates this helium core, tries to expand, but the outer layers of this star is suddenly feeling stronger gravitational pull toward its companion than towards itself. This forces mass to flow to the companion star. And as the star tries to expand and expand, eventually you are just left with that helium core exposed. I call this a stripped star or a helium star. These have many names, but it's a product of binary interaction that has been known for some time. It has been predicted from theoretical models. For example, here are some really old computations, some photos from Göttingen in 1957, when Kippenhahn and his team computed stellar evolution models with the computer at the bottom and read out the output there from the paper at the top. The outcome of these kind of calculations you can see on the right side of this slide. And I'm not going to go much into detail, but this kind of diagram we will look a little bit closer at later. But what they did here in 1967 is the computation of envelope stripping in a binary, and something that I also do today, but rather using a code that was developed in Santa Barbara, a little bit north from here. So let's sum up a little bit. What is really the difference between these helium stars and the regular stars? Maybe a regular star like the sun or so. So a regular star maybe has a temperature between 3 and 30,000 Kelvin. This is a wide range. But the helium stars are much hotter. They are much hotter because they are composed of more dense material, right? They have only helium. And so they have maybe 30 to 100,000 Kelvin surface temperatures. The regular stars are hydrogen-rich, but the helium stars, they are hydrogen-poor, right? They lost that layer. And they are helium-rich because you see the helium. The regular stars are large. They have a large, fluffy envelope. But the helium stars, they are small. They don't have any envelope. And these three characteristics, I will go through them and look at the consequence of these three characteristics, each at a time. But now, to wrap up the part about what is really a helium star, let's summarize. When a star is stripped of its hydrogen-rich envelope through mass transfer or by a binary companion, the helium core is exposed, and this way a helium star can be created. Helium stars are hot, small, and helium-rich. So let's move now from the helium star, what is it, to what about their ionizing photons? I said I would go through each of these at a time, so let's start with the temperature. What does the temperature really do? It changes the energy of the radiation that the star is radiating. So the star is shining in light. Let's look at the spectrum of light. It's called the electromagnetic spectrum. You might be familiar with this. On the low energy side, we have the radio waves. On the high energy side, we have the X-rays and gamma rays. And somewhere in the middle, a tiny little part, that's the visible light. That's what we can see. And so you probably know many of these illustrations that we've seen here. But so a star can shine in most of these wavelengths. And it depends primarily on what is the temperature of the star. So let's look at the sun, for example. How does that radiation field look like? This is a figure showing you the amount of radiation on the vertical axis as function or for each of the energy of those of the light that is emitted, the photons. So this is the sun's radiation field. We have the infrared light over here at the low energy edge. And the ultraviolet light, very little over here, but very dangerous, right? That's what burns you in the sun. And over here is the visible light, where the sun is the strongest. That's where the visible light is. So I find it quite interesting because, indeed, we are made for the sun, right? Otherwise, maybe that would not be the visible light. And so let's look now how does a helium star look like in its radiation field. This is a figure showing how the radiation field of a helium star looks like. And so it's worth it to compare to that of the sun at the bottom corner here. It's actually to scale. So it is in the right energy range, so you can see that there is much more of the really energetic radiation that a helium star emits. So over here is the infrared, that's the visible part, ultraviolet, but what's the rest then? It is ionizing radiation. And what is really ionizing radiation? Let's go through the little cartoon. Here is a cartoon of a hydrogen atom. It is composed of a proton orbited by an electron. And there is a bond between the proton and the electron, really strong bond. But you can dissolve this bond with a sufficiently energetic photon, sufficiently energetic light, an ionizing photon. It makes it disappear, unbinding the proton and the electron, making them go in different directions. So this is really quite harmful for the hydrogen atom, right? You destroyed it. So imagine what happens if ionizing radiation would reach us, or maybe something as fragile as a gas cloud, for example. And so that's what we're going to look at next. Do you remember this part of in the beginning of the universe, when material clumped together, creating overdensities? Apart from the overdensities, there is other things here, right? There is, let's see, this part, that's not really an overdensity, but there is still some material there and here as well. So between stars, between galaxies, there should be leftover hydrogen and helium from the formation process. And this, for example, here, it should be some clouds in between the galaxies. This is usually called the intergalactic medium. And if then these galaxies would radiate sufficiently energetic radiation, you may destroy those clouds. That really affects how these galaxies grow and how the stars in turn grow inside the galaxies. So this is something that actually happened. Here is a simulation of that process. It's called the reionization. So in each of these little bubbles, there are many galaxies, and they emit this really hard ionizing radiation that is slowly ionizing the intergalactic medium until it is completely ionized at this stage. So the epoch of reionization occurred really quite early. If we look at the scale of the universe here, the evolution of the universe, over here at the Big Bang, 13.6 billion years ago, just like a billion years later or so, the first sources, the first stars, galaxies started to form, ionizing the intergalactic medium, giving rise to the reionization that occurred over here. And that is what was the basis for what we see today at present day in the galaxies and populations today. So usually, in the simulations of the cosmic reionization, helium stars are not included, and they often have some problems with producing sufficient amount of ionizing photons. So I thought this was really quite interesting and wanted to explore what could the role of helium stars be during cosmic reionization at early times. And to do that, we're going to look at the results of this exploration. Here is now only considering regular single stars, massive stars. This diagram shows you time in the reverse direction. It's a sort of time scale. And on the vertical axis, we can see the fraction of the intergalactic medium that is ionized. So reionization should occur when we reach 1. That is, let's see, over here, right? So then over here, about 15% or so was ionized, but here all of it is ionized and reionization is finished. The time of now is somewhere over there, so it's very long time ago. If you include the helium stars, the stripped stars, you get earlier reionization. And this is because they provide a significant contribution of ionizing photons early on, is the prediction of my models. So in my models, here you can see it occurs about 100 million years earlier, which is quite a lot at those early times, because the universe was so young, just maybe a giga-year or something like that. And in my models, the stripped stars, they could have contributed 10% or something like this. So that's really quite interesting, actually, and something worth to spend more time to look into in the future. So to sum that up, stripped stars are so hot that they radiate ionizing photons. And they can have radiating so much ionizing photons that they contributed with 10% to the cosmic reionization. So then, let's move on to the gravitational waves, right? So gravitational waves are created when, for example, binary stars orbit very closely. And what they do then is that they create so-called ripples in the space-time that we can observe as gravitational waves. Gravitational waves, just as light, have a spectrum. So here we can see the electromagnetic spectrum in the top just to compare, and the gravitational wave spectrum here shown with the low frequency on the left and the high frequency on the right. You may know some gravitational wave sources, for example, merging black holes. They have been detected recently with the LIGO and Virgo detectors, merging neutron stars as well. So this happened with terrestrial detectors. And it's because they orbit in such short orbits that their gravitational waves have really high frequency. And so then we can detect this on Earth because the detector can be small enough. I was curious about this because technically you should be able to radiate gravitational waves also at lower frequencies. And there are predictions of, for example, double white dwarfs or so to radiate gravitational waves. But all of these are dead stars, right? They are remnants of stars. And in fact, helium stars are sufficiently small in order to be able to radiate gravitational waves if they are in a sufficiently tight binary. And this could be detectable with a future space mission called LISA, which is much larger. We're going to look at that in a little bit. But so from this picture, you might be familiar with the merging neutron stars, for example. Helium stars also play their role because the merging neutron stars don't come out of nowhere. The progenitor went through a supernova, and because it was so tight, it's pretty certain that that was a stripped star once upon a time. So also for the merging neutron stars, the helium stars played a really important role in their creation. And going back to this picture, if we look now at the fact that the regular star is large while the helium star is small, this is why the helium star can fit in such a tight orbit that gravitational waves can be emitted compared to a regular star, which is too large. So to actually detect these gravitational waves, we need a really large detector. And so this proposed mission, LISA, looks something like this, isn't it? A little crazy, you know? It's, we have the orbit of the Earth around the sun, and that red triangle, that's going to be LISA. So with that large, I think 5 million kilometer arms, we can detect this sub-millimeter gravitational, sub-millihertz gravitational wave frequencies that are thought to come from these sources. So I made a model trying to estimate how many are we going to detect with LISA. of these living stars, of these stripped stars orbiting neutron stars or maybe white dwarfs. And so I will show you the outcome of this model here. We're looking at a diagram showing you the frequency of the gravitational wave emission on the horizontal axis. It's a low frequency at the left part and high frequency at the right part. And on the vertical axis is the gravitational wave signal, so to say. So how strong is the gravitational wave? In the white region, Lisa will probably be able to detect any source. If we find a source with that frequency, that strength, should be detectable. In the gray region, that's a little bit outside of the detectability zone for Lisa. So in my model, I found stars ending up basically in the low frequency part of this regime, and quite a large number actually detectable. This depends on several really quite uncertain properties of binary stars. So for example, what is the period of binary stars when they orbit a compact object? Or how small can helium stars really become? So in this simulation that I created, I found 5 detectable systems, and changing these uncertain properties, we can explore what the variation can be, and it can be all between 0 up to 100. But there has already been 2 sources detected. They are marked in black there. So for sure, it is not 0. So wrapping that up, because stripped stars are so small, they fit in really, really tight orbits and can therefore radiate gravitational waves, which can be observable by the future space mission, LISA. So with that, we will reach my favorite part, which is my ongoing research that I am doing primarily with Maria Drought and Bethany Ludwig. So I put their photograph here so that you get to meet them as well. They've done fantastic work with me, and I'm going to show you the first of our results. So we are going to look into where are really all these helium stars? I've been talking a lot about them. What have you ever heard about them? Have you found them? So we wanted to find them. How do you find something that has not been found before? You make some really good testable predictions, right? And you try that. So what's happening here in the background, this is real data from a stellar cluster. And each dot is a star. It's colored according to its color. And its brightness is according to its brightness. So what did we do? Let's do this again. So the stars were now sorted according to its temperature. There, we start the sorting now. And you can see how the blue stars end up on one side and the red stars end up on the other side. And then we sort according to the brightness. So the faint stars end up on the bottom and the bright stars at the top. So we can recognize here temperature axis and the brightness axis. And from before, I told you the stripped stars are really, really hot. So they should be somewhere on the high temperature part of this diagram, right? Probably somewhere there, maybe even brighter. But what you can see from this figure is also that color is really quite a good proxy for temperature. So if we can observe the color of stars, we might be able to understand what their temperature is. But stripped stars are so hot that the visible color is not enough. We cannot just use blue. We need to use ultraviolet, right? So what we did, we went to look at 2 of the nearest galaxies to the Milky Way. These are called the Magellanic Clouds. That's the small Magellanic Cloud, as SMC, And that's the Large Magellanic Cloud, the LMC. They are visible from the southern sky. And as you can see, this image is taken with optical color. But with the space mission SWIFT, also UV data has been taken of the Magellanic Clouds. These are images, and if we look a little bit closer at them, you can see that there is lots of UV sources in the Magellanic Clouds. So that's great, right? Because then we have probably, we can find many candidates and look at whether we can find some of them to be helium stars. So this I thought was really, really fantastic to start with, but I want to show you one of the struggles that we had to go through, which really highlights the importance of precise data. This is an image in visible light. It's colored, is fake, but this is a visible light image, and it's of a part of the small Magellanic Cloud. It's really quite small. So if you, for example, if you hold up your thumb, that's about 1 degree, your thumb on the sky. And if you divide that by 100, that's the extent of this field. So you really need a very good spatial resolution. And this image has it, right? You can see the different stars. You can see the little red dots. That's actually a star we've been observing. It's really hard because there is that blob beside it, and you have to change them. Yeah, anyway. In the ultraviolet, we have a problem, right? So this is the same field. So how do we know which ultraviolet blob corresponds to which star, right? Because there is many sources in each of those blobs. So this is something that particularly Bethany has been really digging into to understand what light came from which stars, with some clever programs that I'm sure that she will explain very soon in the future. And in the end, we managed to extract decent colors in the ultraviolet. These are the results from that survey. Here you can see a diagram not so different from the one on the top that we recognize. You recognize this sequence of the regular stars. That's that sequence. And that means that the stripped stars, they should be located here. And there are hundreds of sources there. This is in the Large Magellanic Cloud. This is in the Small Magellanic Cloud. And you can see there is many candidates that we have discovered, but how do you actually know what they are? How do you know that they are helium stars? It would be a really strong claim to just say, oh, we found them, without checking for sure. So how do you check it? I use spectroscopy, it's called. And, oh, how weird. Oh, well, anyway. This is the spectrum of a helium star. Here showing you, again, the energy and the brightness. So the amount of light as a function of energy. If we look over here, for example, let's zoom in a little bit. This is how that spectrum looks like. So there is some wiggles, some particular stuff happening there. It's not so different from regular barcode. It's really like these different features are characteristic to a specific type of star. So just like a barcode can be specific to an apple or a flower or something like this. So if you have a field of stars, you take your scanner and you go and scan the stars. And then you're like, oh, yeah, that one was a stripped star. Is our idea, right? But okay, scanners work for apples. For stars, we need something bigger. This is our scanner. This is a Magellan telescope. And we used an instrument called MAGE on the Bade instrument, on the Bade telescope. And let's see here. Okay, so for scale, that's a car, right? And here is the mirror. It's huge, 6 meters. So what we got out of that is not just like the scanners saying Apple. No, we got this, and now we have to decode it ourselves. So this, I think, is one of maybe the nicest results, right? So what can we see? This is ionized helium we can see here, those dips. And that's ionized helium and hydrogen. And then in the pink, that's nitrogen. I find it really, really nice because from this, we can measure temperature because of the ionization, right? Higher temperature, more ionization. From the helium and hydrogen, we can measure helium abundance, amount of helium. And these two are really crucial for determining whether the star is in fact a helium star. So are they really helium stars? Let's show the outcome of this. Here is the diagram showing you the temperature from low to high and the amount of helium. So regular stars are somewhere here, right? They were created with a bit of helium, but it was not super much. It's something like that. Helium stars, we predict they should be there. So we took, here we have some stars, some barcodes of stars, and we decipher, and they are located there. So this is the first of our results from this new survey in the search of helium stars. And it's really exciting because it's actually a first population of helium stars discovered. And thanks to the wonderful facilities in Las Campanas, we will be able to determine interesting properties, like what's the orbital period of these systems, what kind of companion do they have, and do they rotate, what kind of, do they have a stellar wind? So we have a lot of interesting things to continue this with. And so to finish up, we have discovered the first population of stripped stars in the Magellanic Clouds. And we are excited to show these first results to you. And I really hope to be able to expand further later on. So with that, I believe maybe I'm a little early, but hope there's not a problem. Thank you so much for your attention.
Thank you for a really fascinating talk. That was really interesting. I always love when I learn so much from talks. I learned far more about helium stars than even I knew. We do have a bunch of questions, so I'll jump right in. Let me start with some of the more basic questions to start with, which is, so you mentioned binary stars. So do you have an estimate for how many stars are in binary systems?
Yes, so this is a nice question. I actually have a backup slide. Here. Oh. So binaries are very common. In fact, 70% of massive stars are thought to be in so close binaries that they will exchange material or even merge as they evolve. So what we can see here is 30% or so will lose their envelope through envelope stripping, create a helium star. About 15% or so is that second star. So why is that not the same? Because this figure was created for the most massive stars, right? So sometimes the companion is less massive. And a quarter mergers. Isn't that interesting? I really like this one, the peanut star. And there has been a few massive systems observed like that. This particular one shares about 30% of its mass in that overlapping region. So yeah, that would be really exciting to better understand as well. So for lower mass stars, slightly fewer are in binaries, leading to maybe 50% of solar type stars. Of those, slightly lower fraction are interacting, maybe 15% or so.
All right, thank you. There's a question about the chemical composition of binary stars. Are the chemical compositions the same for the binaries?
So that's a very good question. This leads back to star formation. So I didn't go into star formation. Didn't go into binary formation. How does a binary form, right? There's two scenarios that we usually consider. One is you have a clump of material over dense region that starts to fragment and create different clumps that orbit each other. Okay, so you should have like any kind of orbits because of this. Or, alternatively, you have one star that is accreting material from a disk, so it's eating material through a disk. That disk is really massive, so it fragments, creating you a sort of a disk-like system, not so different from the sun. So in these scenarios, probably the two stars in a binary should have similar composition to begin with, right? But as they evolve, that changes. If you create a helium star, clearly the helium star has a different composition from its companion. But the companion can also have a different composition compared to initially, right? Because it accretes a lot of material. It can even be helium-rich, nitrogen-rich.
Excellent. There's a question about the location of helium stars. This is from Phil. He wants to know, are helium stars expected to be more frequent in the inner or outer part of a galaxy?
Good question. So this leads back to how old are helium stars? What mass of stars create helium stars? So if helium stars can be created from really low mass stars live for very much time. So then you can find helium stars in really old regions, which tend to sort of create the structure of the galaxy. Most of the helium stars that provide most of the ionizing flux, they come from massive stars, really massive stars. So they should be in star-forming regions. In our galaxy, that's the disk, primarily. But there is a lower mass version of these helium stars. They are called the subdwarfs. And the subdwarfs provide a lot of UV radiation, have been found in elliptical galaxies, old elliptical galaxies, with providing light that has been referred to as the UV upturn, for example. So this depends primarily on what kind of helium star you're interested in, I would say.
Yeah, excellent. So there's a question about, there's one year slide 37, which is the slide of the spectrum that you took recently at Magellan. Mm-hmm. I think that's 37, is it?
Yes.
And the question is so I think the question here has to do, are we seeing these lines in absorption or emission? So it's absorption, but maybe, yeah.
Yes, I will elaborate.
Yes,
there is actually one emission line too. You can see them.
Oh, there is an emission line. Yeah.
Yeah. Okay.
I missed that. Yeah.
Most of them are absorption features, and that's unexpected actually. I didn't show you my model from before. My model from before showed some emission features here, and this has to do with how strong the stellar wind is. So because we didn't have observations of helium stars prior to this survey, we had no idea how strong is the stellar wind. So if the stellar wind is strong, there should be emission lines, features going up here. If the stellar wind is weak, we see absorption features. You see the surface of the star. We primarily see the surface of the star here. The the emission features there, they come from detailed photospheric effects that are due to, I think it's level pumping. It's some detailed physics that is creating these emission lines. So they are not necessary. They don't come from the stellar wind. This star has negligible stellar wind.
And so related to this, Richard asked the question, he wants to know why there's nitrogen. Mm. In other words, are the helium stars, they're not 100% pure helium necessarily, right?
True. I skipped that part, but let's go back to the stellar evolution. So we had during the hydrogen fusing into helium, in massive stars, the hydrogen takes help from carbon and oxygen to create helium. And what happens with carbon and oxygen is that it is converted into nitrogen. So the carbon and oxygen that was already in the cloud when this star was formed becomes nitrogen. And so you get a nitrogen-rich core. This is not rich in terms of the amount of helium. This is some fraction of 1%, but it's enough to show features in the spectrum of the star. And I should say, I didn't put carbon, nitrogen, and oxygen in the cloud when I said that stars are formed. And so actually, in the beginning of the universe, there was not carbon, nitrogen, and oxygen. So then the stars, they couldn't burn like that. They couldn't do that nuclear fusion. And so those are really special stars, right? They called Primordial Stars, population 3 stars, completely metal-free. But this goes through a slightly different nuclear reactions usually.
Yeah, so the stars you're looking at actually are not that first generation of stars. They've already evolved. They've already come from material that involved previous generations with oxygen and nitrogen being created. Yeah, excellent. And then I had a question, which is, I'm wondering why did nobody else find all these helium? So you're finding these helium stars using Magellan, which is great. And the question is, why did people not find them before?
It's because of this. So, because it was, so first, there was not a survey for helium stars. There were surveys for other hot objects and like more exploratory searches, but you need to figure out the UV contribution from each of the stars in order to get out some reasonable data, right? You cannot just have some random number here. So this programming that Bethany and Maria have been doing for the ultraviolet images has been really important to be able to find accurate candidates.
And I guess a related question is, you're looking in the large and small Magellanic Cloud as opposed to the Milky Way. So I was wondering about that. Have there been searches for helium stars in the Milky Way? Have they been found, or what? Yes.
There is, first, there's one stripped star known.
One?
One.
Wow.
It is called HD 45166, and it doesn't look like those. It's a peculiar one. It has some extra wind, some disk, and it's seen almost pole on. And that's in the galaxy. It has really strong emission features as well. It's about 4 solar masses. It's measured through dynamical motion, so it's very accurate measurement. But apart from that, there is nothing. Why? Because it is really hard to know the brightness of a star if you don't know the distance very well. So something that is bright, like the lights on me here, if they were a little bit further away, they wouldn't look so bright, right? So if I would know, okay, I know that this is about, maybe 12 meters, and if it's a little bit further away, it would be less bright. But if you want to know the intrinsic brightness, you can place them in this diagram, and you can figure out, is it that it's just fainter, or is it more massive object? So you can do this in the Magellanic Clouds, because we know the distance to these galaxies. But the Milky Way is really hard. We don't know the distance to many stars. Accurate enough in order to be able to place it in these kind of diagrams. Also, we live inside of the disk of the Milky Way. And the disk of the Milky Way has a lot of gas. So if you want to look into the other star-forming regions of the Milky Way, there is lots of gas and dust in the way. So it can be really hard to see how hot stars are, because they don't have the right color. They have some redder color than they are supposed to have, just because of the dust or gas in the way.
So we're really quite fortunate that we have these two little galaxies and that they're out of the plane so we can actually see them.
Yeah.
To do these sorts of experiments. Yes, we got quite lucky. Excellent. The last question, because it's really hard to give an astronomy talk without asking about planets. So there's, of course, people are curious, would helium stars have planets? How would they might be different? I know this is not your expertise, but...
No, that's an interesting question.
Sure
I would love that to be my expertise, but it's not. Let's see. So here, and then maybe put it with the spectrum of the sun. So, I mean, we have a lot of ionizing radiation here, which can be a problem. I would love there to be planets formed around these helium stars. But I wonder if it's possible, because it has this destructive, really strong destructive radiation that may destroy any clumping surrounding the star. Also, we have a timescale issue, which is that these stars are created when the hydrogen fuel is depleted, right? So then the star lived most of its life, and if you have an interaction, say it's a sort of messy interaction, expelling lots of that envelope surrounding the binary star, and actually manage to create a disk, you still have less than 1 million years-ish to create planets from that disk. So that depends on the mass of the star, how much time it has left to live. Maybe the low mass versions have planets. And I know that subdwarfs, they have searched for planets orbiting subdwarfs, but it has not been successful yet. We'll see.
Yes, and of course, if you had a planet, so a related question, which you somewhat addressed, of course, if you did have a planet here, somebody asked about the habitable zone. Of course, I mean, you have all these X-rays and ultraviolet, so it would probably not be a great place to have life.
Yeah, who knows what life thrives in,
That's
right?
true.
But
That's true, right, yes.
No, certainly humans might be in the danger zone around a helium star.
Yes, I always remind people the universe always surprises us. So you might think that this, even though I'm saying it might not be a great environment for life, you just don't know what the universe can create. Well, Ilva, thank you. This has been really fascinating. Hopefully everybody learned a lot about helium stars and binary systems in general. It's a really important topic in astronomy, as you hear, and we look forward to seeing your new exciting paper on the results very soon. I'll remind everybody that we're back for our final lecture. The reschedule of Andrew Newman's lecture is 2 weeks from today, 4 p.m. Pacific time, and we look forward to seeing you there. And thank you everybody for joining us, and thank you, Ilva, again for a great talk.
Thank you.
Bye-bye. Yes.